Okay, so let me go over about on the time complexity analysis and some examples, and then if you have any specific questions you can ask me after that. Okay. Uh, so basically what we are doing here is, so when you write your program, uh, you want to write more time efficient program. You don't want your program to run forever. So for that it's very important to have an understanding of how long your program will run before you start typing your code, and that's the purpose of what we are going to do now. It's called the theoretical time complexity analysis. Means like without really writing the actual C++ or any program in any language, you are going to write what is called like an algorithm, a pseudo code of it, and try to find out theoretically how long it will take. By theory it means, I mean, like the as a function of the input size, you are kind of estimating in general how long it will take. And also we are focusing on, as the input size gets larger, means you're running a very large data set, larger input size, how long your program will run as a function of that input size. So things will be kind of in an abstract fashion. By abstract I mean we won't see numbers for input size, we will see the input size is n, like that. Okay, so that is something you have to be familiar. Okay, so we'll start with a very simple example of trying to search for okay, why this let me see. Okay, so we will look at a specific example of trying to search for a key in a given array. Key means any element in the array. So let us say you're given this array and you want to search for a specific key. Now, so the first thing we should come up with is the logic. How would you do this? Okay. So you're given the input is the array from index 0 to n minus 1. So if your array has 8 elements like this, the index will range from 0 to n minus 1, which is 7. Let me see.
That's why
What? Okay. Then you are searching, say, for a specific key, say key 8. Then what would you do? That's what we have to decide. So you could go through a very straightforward approach of going through this array element by element and see if you found the search key, which is say 8. So the logic would be to start with index 0 and compare 8 with 5 and see if they are the same. If they are the same, we are done, we have found the search key. If they are not the same, you just keep searching the next index. So next index is 1, compare 8 with 7, are they the same? No, just keep going. So when you reach index 4, 8 is same as 8, so you have found the search key and you can stop the program. So this is a high level logic explanation. If you are writing this as a pseudo code, you write a for loop for index. So this is not C++ or any language, this is just plain English. And you may ask, what is the syntax for writing a pseudo code? There's no particular syntax. You could follow as if you're writing in English, but just as a convention, will make it look like a loop or make it look like an if statement and so on. So we can say for I equals 0 to n minus 1. So I is the loop index. And this do is, again, it's not a keyword, it's just to tell that, okay, we are going to do all the things inside this for loop following that. So now if we find the search key, how do you check if you find a search key? If a of I equals the search key k, like we found search key when index is 4, we can say the key is found at index 4 and stop the program. So return is like coming out of the algorithm. and returning whatever the output you expect it to be. Now, if not, so if and if means if you start doing something if the condition is true, and then you put an end if. Again, nothing is like a keyword, just like a more formal way of telling things. So you begin the if block and end the if block. Similarly, you don't have anything else to do inside the for loop, just keep checking that for every index. So end for. Now, if you are not able to find the search key, then you would search every index in the array and then come out of the loop and say return key not found. So that's the only time you'll really come out of the loop. If your search key is there, you would just stop the program and come out of the program within the loop itself. Okay. Any questions so far? Okay, so this is the logic, and we explained that the pseudocode. So now we need to estimate how long this algorithm will run. Now it looks like it depends really where the search key is, because if the search key is at the index 0, we would have stopped just by looking at index 0. If the search key is say somewhere in the middle of the array, we have to go through until that index position. If it's not there, we have to go through the entire array. So that means we can say there is a best case scenario and a worst case scenario for the time the program will take. Now, in order to analyze that time, we are not going to run the physical time, a clock or something, and measure the time. We are going to analyze the time complexity based on the operation that we do repeatedly. So that's called a basic operation. So a basic operation means that operation that's most time consuming and is also done repeatedly in the algorithm. And looking at the pseudocode or the logic that we come up with, we have to identify what is that basic operation that we do repeatedly in this code, and should also be the most time consuming. So typically the operation will be inside a loop if you have a loop. If you don't have a loop, again, if you can go through the code and find the most time consuming operation, which is typically in the order of like multiplication, division, or more time consuming than addition or subtraction. If you take exponent like 2 raised to 3 or 2 raised to I, something like that, then that's also more time consuming, and it's even more time consuming than multiplication or division. Now here we do comparison, that is the most time consuming operation in this pseudocode, and it's done repeatedly for every index I. So we have to now analyze how many times we do this comparison. Now if the search key is found at index 0, we'll just do one comparison. If it is found at the last index, or if it is not in the array, then we have to go through the entire array. So that means for each index I, we'll be comparing the value at index I with the search key. So that will be the number of comparisons we are doing. So at the worst case, we'll do n comparisons. Okay. So that is how you come up with the best case and worst case number of times we do the basic operation for an algorithm. Any questions so far? Okay. Alright, so let us go back. Now, let us look at one more algorithm. So this is the problem of finding a maximum integer in an array. So again, you are just given an array and you want to find the maximum element in it. So let us take the same example here. So you would have done this as a program in 118, and the logic you would have typically come up with is use a temporary variable as the current maximum or estimated maximum in the array, and assign that or initialize that with the first element in the array, which is at index 0. So max is a of 0, and then go through a loop. So since we already have max assigned to a of 0, it's just sufficient to start the loop from index 1 and go all the way to end of the array. Now as we go through the array, if we happen to find some element at index I, that is greater than maximum, we can set maximum to be that element at index I. So that's the if statement, where we check if the current value of maximum is less than a of I. That means some element at index I is greater than maximum. Then you can set max to be a of I. So as we do this check, so initially we start, say in this case, with 5 as the maximum, and then we come across 7, so 7 will be the maximum. Then at index 2 we have 3, which is not greater than 7, the current maximum. So we'll keep it 7 as the maximum. Then index 3 we have 1, which is again not greater than the current maximum 7. Then we come across 8, which is greater than 7, so we update max to be 8. Then we come across 10, which is greater than 8, so update max to be 10. And then 2 and 9 are less than 10. So once we reach the end of the array, we will have the global maximum, the maximum across the entire array in this variable max. So you can return max after you come out of the for loop. So again, this is like very similar to C++ code, but we don't have to really worry about the syntax. We want to capture the idea and write it like in the pseudocode fashion. Now we can again analyze the time complexity. The first thing is we have to find out what is the basic operation, which is the operation that is done repeatedly. So if you look at it, there's a loop, and inside the loop we are checking if a of I is greater than maximum. So that is the operation that we do repeatedly, the comparison operation. And again, irrespective of where the maximum is, according to this logic, we have to really scan the array from index 1 to n minus 1. It could be that element at index a of 0 is the global maximum, but still we have to check by comparing it with every element in the array. So that means the best case and worst case will be the same. And what is that number of times we do the comparison? So for every index from 1 to n minus 1, we do the comparison. So that means the number of comparisons is essentially how many comparisons are ranging from index 1 to n minus 1, basically n minus 1 comparisons. So that's the best case and worst case. Okay. Any questions so far? So we saw two examples where in one of them the best case is different from worst case, and in the other one the best case is same as worst case. So now we need to convey what is the overall time complexity of this algorithm, and for that we are making use of this asymptotic notations. Okay, so let me now get into the two asymptotic notations. So if you have, say, a function, say 2n squared plus 3n plus 5, we want to say at the what is the upper bound, how this function grows as n increases. Basically that's what we want to look at, how this function will grow as n increases. Now if you look at it, as n increases, the lower order terms basically become insignificant compared to the most dominating term. So when I say most dominating term, it's the degree of this polynomial that decides which is the most dominating term. So in this function 2n squared plus 3n plus 5, n squared is the most dominating term. So we can simply discard the lower order terms and say 2n squared is the most dominating term. And we can also discard the coefficient and simply say n squared. So this function grows at the rate of n squared. Now if you want what is called a tight bound, then we should simply say this function equals theta of n squared. So this function strictly grows at the same rate as any n squared function. So I could come up with some function, say 5n squared or 10n squared, and that function as well as this 2n squared plus 3n plus 5, they grow at the same rate, because as n increases, it is the n squared term that is the most dominating term. Okay. Now that is giving you a tight bound. Now if you want like a loose bound, in the sense that we want to say at the worst case this function will not grow beyond some other function, then we can still say that is big O of n square, but that's not the only function we can come up with as an upper bound. Even n cube is a function such that 2n square plus 3n plus 5 will always grow less than n cube. It will not go beyond n cube. So if we want a loose bound, then we can use the big O notation. So this is the key difference. So if you want a tight bound that tells the exact rate the function will strictly grow, then we have to use a theta notation. So given a function polynomial, we have to first find what is the most dominating term and just write that whatever we end up with inside the theta notation. So how we do that? Discard the lower order terms, and we still just have 2n square, discard the coefficient, and we finally have n square, and that is theta of n square. We can say, once we say that theta of n square, we can also say it is big O of n square, because for big O, the function on the left hand side should grow at the same rate or less than what is inside the big O notation. In this case, when you say it is big O of n square, they grow at the same rate. But if you say it is big O of n cube, the function on the left hand side grows less than the function inside the big O notation. So the function that goes inside the big O notation is like the upper bound function or the big guy. You always think like that. So the degree of the polynomial that will have inside the big O notation will be greater than or equal to the degree of the function polynomial on the left hand side. Okay, so any question on the big O and theta notation? So feel free to ask. Okay. Okay, so let us do couple of more cases for the big O notation. So if I have 4n cube plus 3n plus 5, how to come up with a theta and big O notation? Again, the first step is to discard the lower order terms, and we'll discard the 3n and 5 because they do not grow as fast as n cube as n increases. So again, we focus on asymptotic means as n increases, as n grows larger. So we are left with 4n cube, and again discard the coefficient, and we simply have n cube. And right away we can say that is theta of n cube, which also means we can say that is big O of n cube. So if we can say something as theta of a polynomial inside, we can say use the same polynomial that we have inside the theta notation also inside the big O notation. So that's why I said theta implies big O. Now once we decide that, any function that grows even faster than n cube means even larger. So anything like n to the power 3.1 or n to the power 4, n to the power 5, anything that can even grow faster than n cube can also go inside the big O notation. So we can say 4n cube plus 3n plus 5 is big O of n to the power 4 or n to the power 5 and all those things. Now theta implies big O. So that means if I say this function is big theta of n cube, that is also big O of n cube. I can say 4n cube plus 3n plus 5 is big O of n to the power 4 because the function on the left hand side grows less than or equal to the function on the right hand side. But that doesn't mean I can say that is theta of n to the power 4, because if you use theta, the degree of the polynomials on the two sides should be the same. So here the degree means the largest exponent value is 3, whereas here it is 4. So we cannot use the theta notation if the degree of the two polynomials are different. So only if they are the same, then we can use the theta notation like this. So that's why big O need not imply theta. So it depends on what is inside the big O notation. If you have n cube inside the big O notation, yes, we can use theta notation also because they are the same degree on both sides. But if you have n to the power 4 inside the big O notation, we cannot use that as theta of n to the power 4. So that's why I have the statement theta implies big O automatically, but big O need not imply theta. Okay, so any question on this? So now what all just is remaining is putting things together. So we saw the two example sample algorithms, and we came up with the best case, worst case for each of them. And we now need to put together and say that what is the asymptotic time complexity of these two algorithms. So the thumb rule is this: if the best case is different from worst case, that means they are really not comparable to each other. So think about it. So if n, the size of the array is say 1 million, then at the worst case we'll be doing 1 million comparisons, whereas at the best case we do one comparison. So they are not really comparable to each other. So then we have to indicate the asymptotic time complexity of the algorithm using the worst case number of times we do the basic operation. So in this case it is n. So we have to use the big O notation and write what is the worst case inside the big O notation. So that's why I say for this first algorithm out there, the time complexity is big O of n. And we cannot say theta of n because the best case is not the same as worst case. On the other hand, for the second problem, for the maximum integer problem, the best case is the same as worst case, and that was like n minus 1 comparisons. So if the best case is same as worst case, we could use the theta notation. That's the most appropriate notation to use for asymptotic time complexity. So we can say it is theta of n minus 1, that is the number of comparisons we got for the this algorithm. Now again, inside the asymptotic notation, the convention is we will just have one term, the most dominating term. Now in the expression or function n minus 1, 1 will not grow as n increases. It is n that will grow. So we can discard the lower order term, which is this 1, and just keep the higher order term, which is n, and say the time complexity is theta of n. Okay. So if for some other algorithm the time complexity comes out to be this, this is the number of times you do the basic operation, 2n square plus 3n plus 5, and we go through the same process, discard the lower order term and say that is theta of n square. Okay. Any question on this? So this is really the big picture that you need to understand. So given an algorithm, you should be able to analyze the working of the algorithm, the pseudocode, and then find out the basic operation, find out whether we do the same number of times, means the best case and worst case are the same or different. So what is that best case and what is the worst case? And if best case and worst case are different, use the big O notation and write the worst case number of times you do the basic operation inside the big O notation. If the best case is same as worst case, use the theta notation and write whatever the number of times you do the basic operation inside the theta notation. And make sure you have just only one term inside big O or theta notations. So it means discard the lower order terms, discard the coefficient of the most dominating term, and just write the n, and whatever is a function of n inside the asymptotic notation. Right? Any questions so far? Okay, so we'll do one more example, which is this printing problem. So here I'm given an input which is say n, and then again, as I said in the beginning of this lecture, the pseudocode is just like in English, how you express your logic. So there is no keyword or no particular syntax you really have to follow. But as a convention, we'll follow the programming style. So if some condition is true, so you put it in some parenthesis, and then is again not any keyword. You just say if this is true, then we will do something. So then what we'll do, so do some indentation and write what you'll do if the condition is true. So here we have a for loop that runs from index 1 to n. So again, there's no particular syntax to write the index, how you write the things inside the for loop. You just say I equals 1 to n. Okay. You can say I ranging from 1 to n. You can put your own English word, but that's also okay. So just as a convention, we'll write like this: the index I going from 1 to n. Then, so in this pseudocode, I'm just telling I'm printing a statement, and so it's one statement that gets printed. So I say it's printing so whatever the time it takes, I say it's unit time. Okay. So we don't have to really measure that time. Just say print the statement, and it takes one time unit to print one statement. Then you repeatedly print that statement for each index I. You print it once. So basically, since the loop is running from index 1 to n, you will print it n times. That's the number of times the statement gets printed if this condition is true. If the condition is not true, you will have to go to the else part of this code, and inside the else block we are writing, say, a nested for loop, and that is for I going from 1 to n. That means that's like a loop index. Now for each value of I, you do what is inside that outer for loop. So you have another for loop where you say j equals 1 to n, and you print a statement. That means for given I, you run the j loop from 1 to n. So if I is equal to 1, you are going to print n times the statement. If I equals 2, you are again going to print it n times. If I equals 3, you are again going to print it n times. So I can go from 1 to n. For each value of I, you are going to print n times. So basically then you will be printing n squared times within this else block. So this is given a pseudo code. You have to understand the working of it, and get a feeling of what is this algorithm trying to do. So basically this algorithm is trying to print a statement either n times or n squared times. If the condition inside the if statement is true, then the program will print that statement n times. If the condition is false, it's going to print it n squared times. So that's the big picture of this algorithm. So once you decide that, we want to go ahead and analyze the time complexity. And for that we need to find out what is the basic operation, which is the operation that is done repeatedly and it's most time consuming. So we have loop to do things repeatedly, and what we do inside the loop here is printing the statement, and that's printing is a time consuming operation, so we can assume that is a basic operation. And as I explained earlier, we are not printing the same number of times. It depends on whether the condition is true or not. If the condition is true, we are going to print it only n times. If the condition is not true, we are going to print n squared times. That means the number of times you are printing is not the same for a given n. It depends on, again, I have not given the condition. The condition may involve n, and depending on that you may print. So it depends on what the condition is and what the input is, and we are not really going to need to worry about those things. According to this pseudocode, it looks like there's a best case, basically, according to which you'll print n times, and then there's a worst case for which you'll print n squared times. So that's what we have to need to identify. So that means the best case is different from worst case. The best case number of times we do the printing, the basic operation, is different from the worst case. That means the time complexity can be expressed only using the big O notation. We cannot use the theta notation because best case is not same as worst case. So what we write inside the big O notation is the worst case complexity, which is n squared. Again, this is the only term in the worst case number of times you do the basic operation. If you end up having n squared minus 2 or something like that, then you will discard the 2 and simply write n squared. If you end up having 4n squared plus say 5n plus 6 or something, again, as n increases, the lower order terms 6 and 5n will be insignificant, and within 4n squared we have to discard the coefficient and simply say it's n squared. So that's what we write inside the big O notation, just that a function of n without any coefficient or without any lower order term. Okay, right? Any question? So basically that's what is you need to understand about time complexity. Okay, rest, just for more details, I have given you some other additional information. So if you are given some functions like this, you need to have an understanding of which function typically grows slower and which function grows faster. So as you say increase the values of n from 10 to 10 squared to 10 cube and so on. So the order in which I've written the functions here, they are in the increasing order of growth, in the sense that the log n is the slowest of all the functions. It will grow, its values will be very small, and as n increases, its values will increase very slowly, whereas the other functions will relatively increase faster, and as you go from left to right. So that's what I'm showing here. So log n, so as if n is 10, log n is 3.3. If n is even 1 million, 10 to the power 6, log n, again this is to the base 2, and again the basis doesn't matter. You can have any base for the logarithm, still it is a slow growing function. So log 10 to the 6 is 20 to the base 2. So you see, even n increases from 10 to 10 to the power 6, log n increases only from 3.3 to 20. So it's a very slow growing function. And then you have the n itself as a function, and it increases at the same rate of this n. Now n log n, so this is like, so once you know about log n and log n and n, we can talk about n log n quite easily, because you see you are multiplying n with log n. So n log n will grow definitely faster than both n and log n. So that's why it is placed next to n, and this is how it is. Now what about n squared? Now again, in the next course 323, we will look at more mathematical way of deciding given two functions n log n and n squared, how to decide which function grows faster. But in this course, just by knowing that log n grows slower than n, right? So that means n times log n, so n multiplied by something that grows less than n will grow less than n squared. So n multiplied by something less than n is going to be, so if I want to show this like this, so we have n multiplied by something that is less than n is going to be eventually less than n squared, right? Because n squared is n times n. So n multiplied by something less than n is going to be less than n times n. So that's why we say n log n grows slower than n squared. Okay, so and you can put the numbers and check if that is true. So substitute n is 10, you can have 3.3 which is log n times 10 which is n is 33, less than 10 squared. Then you have 10 squared, again you have 6.6 times 10 squared is less than 10 to the power 4 and so on. So just try to interpret it like what I just explained. N multiplied by something less than n, the value of this product is going to be less than n times n. And once we know this, we can compare n squared, which is n times n, with n cubed, n times n. So as n increases, n squared will grow less than n cubed. Okay, and n cube will grow less than n to the power 4 and so on. Now out about these two functions. So here in the functions that you have seen so far, what is in the exponent of these functions? It is a constant, either a 2 or a 3 or a 1, like that. Whereas here you have a variable n itself in the exponent, so 2 to the power n. So as n increases, the value of this function 2 to the power n will just explode, will just increase significantly. Okay, so it's an exponential function. So like for example, if n is 10, 2 to the power 10 is 1024, which is 10 cubed approximately. 10 square 2 to the power n is significantly large. It is much larger than any of these values listed here. So that's why we say these functions are very slow compared to 2 to the power n. So exponential is a very time consuming function. And factorial is also a very time consuming function. So this is some additional information for you that when you design an algorithm for a problem in this course or in any course, you should try to make it like what is called a polynomial function of the input size n. You should not make the algorithm to work as a exponential, the time complexity should not be an exponential function of the input n. Okay. So that is why when you have two algorithms, so if you have one algorithm only for a problem, you analyze the time complexity and find out how much it will take theoretically and then go ahead and implement it. But if you have a choice to pick an algorithm for a problem, you should pick the algorithm that will take less time. So again, as I said in the beginning of this lecture, before you write a single line of actual code in a particular programming language, you should have a complete idea of how long theoretically the algorithm will take as a function of the input size n, because that's what you will also see in reality depending on the inputs that you pass to the program. So in this example, we have the problem of finding whether a given integer is prime or not, and if you remember what we did in class, we saw two logic for that. So we went by the simple definition of a prime integer. So an integer is prime if anything other than 1 or n cannot divide. So for example 11 is prime because only 1 and 11 can divide 11 and the remainder is 0. Anything from 2 to 10 cannot divide 11 and the remainder will not be 0. So that's what you are going to check. You're going to check every integer from 2 to n minus 1 and check if the remainder is 0. If the remainder is not 0, then you keep continuing. If the remainder is 0, we can stop and say that n is not prime. Okay. So basically here then we do division repeatedly. That's the basic operation. And how many times we do the division depends on how many times you run the for loop. So you run it from 2 to n minus 1. So the number of times we run the for loop can be considered as n minus 1 minus 2 plus 1. But you should think about it. If you find n to be not prime, we can stop right there. We don't have to really try for all values of I. So you might have done this in 118. So given an integer, write a code to find out whether it's prime or not. So if you're given say an even integer, say 20 like that, it is divisible by 2. So 20 mod 2 is 0. So we can stop right there and say 20 is not prime. So we just do one division for I equals 2. If you are given say 21, 21 mod 2 is not 0. So you try for the next value of I, which is 3, and 21 mod 3 is 0. So you can return right away 21 is not prime. So we do two divisions in that case. So it really depends on what integer you are given. So that means when you say it depends on the input, how many times you do the basic operation, that means you have best case different from worst case. So the best case is doing one division primarily for all even integers, and the worst case is if you're given a prime integer. So if you're given a prime integer, then you have to try for all values of I from 2 to n minus 1 and then say that n is prime. So at the worst case, we'll be doing n minus 1 minus 2 plus 1. So this is a mathematical way of finding how many integers are inclusive in this range from 2 to n minus 1. So as a formula, you can always think like this. So this is the lower limit 2 and this is the upper limit n minus 1. So the formula is upper limit minus lower limit plus 1. So that's the number of integers from 2 to n minus 1. So if you want as in numbers, how many integers are there from 2 to 11? So you can count 2, 3, 4, 5, 6, 7, 8, 9 and 10 and so on. So in order to get a count of this, we can use this formula, upper limit minus lower limit plus 1. That's going to be the number of integers in the range from 2 to 11, including 2 and 11. Okay, and that's what I have written here. So essentially the worst case is n minus 1 minus 2 plus 1, which is n minus 2, and as n increases, this is approximately n. So we'll do n divisions with this algorithm. The other algorithm is there's a math property that if you want to find whether an integer is prime or not, you don't have to go from 2 to all the way to n minus 1. Just check from 2 to square root of n. If no integer in this range can divide n, then n is actually prime. And if any integer in this range from 2 to square root of n can divide n and the remainder is 0, we can say n is not prime. So if you analyze the number of times you do the divisions here, at the worst case is square root of n, again the upper limit minus lower limit, which is minus 2 plus 1. So again this is square root of n minus 1. For larger n, you can discard the lower order terms and simply say square root of n. Now you may think, is that really important? Because why can't I just go ahead with this first algorithm? But you see the time complexity. At the worst case, you're doing only square root of n divisions in the second algorithm, whereas in the first one we'll do n divisions. And if you write down the different values of n, the first algorithm runs for n itself as a time complexity. The second one runs as square root of n, the worst case number. So you see the numbers are much smaller than n. So that's why it's very important to choose the algorithm that takes the lowest amount of time in the worst case. And if the best case is different from worst case, the best case same as worst case, still you need what is that number of times you do the basic operation, and go for that algorithm that does the lowest number of times the basic operation. So this is an example where given two algorithms for same problem, you should find out the number of times you do the basic operation for both of them, and if the best case is different from worst case, you have to focus on the worst case and pick that algorithm that does the fewest number of times the basic operation at the worst case, right? So with that, I really want to see if any of you have any questions. No questions? So this is the first time I'm recording in Zoom, so I'm going to, it said it's going to post somewhere in the cloud, so I'll find out and I'll post that link in Canvas. And I'm also recording on my desktop, so I'm going to post that video also. And I already recorded 2 videos and I posted in YouTube. So all these things will be really going to be helpful to understand this material, which is not really anything complex. So just you have to work it out. The algorithms we just went through, which are very simple algorithms. Okay. So, and as we do the coding in this course on data structures, which we started with list, we'll be coming up with several cases or scenarios where we have to understand the algorithm and analyze the best case, worst case, and stuff like that. So we will be doing this repeatedly in this course. So as you do more, things will get reinforced more effectively, and you'll be able to get the idea. Okay, but with all these things that we went through, you should be able to get the most important concept behind all these things, right? No questions? Okay, in that case we'll stop the session, and we'll meet on Tuesday for the class, regular lecture at 12 o'clock. So I'll post this, so once it is available in the cloud, and I'll post the link. Okay, all right, have a nice weekend, and we'll meet next Tuesday at 12. Right, so I'm going to stop the session. And if there's any question, no questions, right? Okay. Thank you.